Good afternoon, everybody. Sorry for that short delay in the beginning. My name is Teresa, and I would like to welcome you to the 24th webinar in the RUS series. This month, we will look at Typhoon Hagibis through the eyes of Sentinel-1 satellite. And again, as always, this webinar is going to be recorded, and you will be able to repeat the exercise by yourself, so don't worry. And we will also give you more information about this a little bit later. So first, just a quick outline of the webinar of today. First, I will say a few words about the RUS service. For those of you who have already attended the webinar, this will be familiar. And then I will say a couple words about Sentinel-1, as many of you have noted that you're beginners with Sentinel-1 data. And then I will move on just a quick introduction, or not introduction, but quick information about Typhoon Hagibis, when it occurred and so on. And then we will move on to the exercise and Q&A session as always, and it will take us approximately 1.5 hours. So again, as I mentioned in the beginning, this webinar is being recorded, and you will be able to watch it again on our YouTube channel or on our RUS training platform, which I will show you in a minute. So let's start with the RUS service intro. So for those of you who are already familiar, this will be a repetition. However, RUS stands for Research and User Support for Sentinel Core Products. And it's a program that's funded by the European Commission and managed by the European Space Agency. And its main goal is to increase the uptake of Copernicus Sentinel data and support R&D activities. The service provides free and open scalable platform in a powerful computing environment, hosting a suite of open source toolboxes pre-installed on virtual machines, which allows you to handle and process data derived from the Sentinel satellites. So apart from the virtual machines, we also offer a specialized remote sensing help desk. You can ask us all kinds of questions you can have about the use of Sentinel data, for example, which data to choose for which application, and so on. Then we also have a number of training activities, such as this webinar, and also face-to-face events. You can find out more about both, about the virtual machines on the RUS-copernicus.eu website, where you can register, request a virtual machine, and learn more about the RUS Copernicus service. And about the trainings, you can find more on our RUS-training.eu platform, where you can find our future and past training events and recordings from our past webinars as well, and also our e-learning portal, where we publish lectures regarding Earth observation for various applications. Okay. We also, as I mentioned, have a YouTube channel, which is called RUS Copernicus Training, and all our webinars are recorded and uploaded to this YouTube channel as well, so you can watch them there. Just one thing, we usually publish a Q&A summary document, which is not published on YouTube, but is published on our RUS-training.eu website, where also the videos are available. So if you are looking for this document, you have to go there. Okay, so now a few words about Sentinel-1. So as I mentioned, for this exercise, we will be using SAR data provided by the Sentinel-1 satellite constellation. And the Sentinels are a family of satellites built by the European Space Agency for the needs of the EU Copernicus program. The Copernicus program is the largest Earth observation program in the world to date, and all its satellite data are available under free and open policy to everybody for any sort of application or purpose. Once completed, this program will be formed by 6 constellations. Each will have 2 satellites with the different range of technologies, from SAR to multispectral imaging, to get as full image of the world as possible. The Sentinel-1 is the first one of the 6 families, and the constellation is formed by 2 identical satellites, Sentinel-A and Sentinel-1A and Sentinel-1B, and they are placed in the same orbit, phased approximately 180 degrees of each other. The constellation allows a repeat frequency of 6 days over Europe, the Mediterranean, northern coast of Africa, and also parts of the Antarctic. For the rest of the world, the repeat frequency, for the rest of land masses in the world, the repeat frequency is 12 days. The satellite acquires data in 4 different modes, and those are strip map mode, interferometric wide swath mode, extra wide swath mode, and wave mode. And the primary modes are the IW, so interferometric wide swath mode, with VV and VH polarization over land, and the WAVE mode with VV polarization over open ocean. The extra wide swath mode is primarily used for wide area coastal monitoring and including, for example, ship traffic, oil spill monitoring, and sea ice monitoring, also primarily in polar regions. And the SM mode, or a strip map mode, is only used for small islands and on request for extraordinary events such as, for example, emergency management. The spatial resolution differs by mode, and the data are available in 3 data products with different level of processing. The first one is a single look complex, the second one is ground range detected, and then we have level 2 ocean products. I will address the former 2 later, as we will be using them in this exercise. Okay, so and the next step, let's say a few words about the typhoon that we are going to look at. So today we will be looking at Typhoon Hagibis. It was the biggest typhoon to hit Japan in recent decades, and it was considered to be the most devastating typhoon to hit the Kanto region of Japan since Typhoon Ida in 1958. The system reached tropical storm status late on October 5th, as it traveled westwards toward Japan, and it intensified rapidly and reached Category 5 equivalent typhoon on the 7th of October. After maintaining the peak intensity for about 3 days, the Hagibis began to weaken due to less favorable conditions. And on the 12th of October, Hagibis made landfall at the Itzu Peninsula as a Category 2 equivalent typhoon. And then it became extratropical on the following day. So, let's have a look at the exercise. So first, just which data are we going to be using and why? So with extreme events like this, I'm not sure why the video is not running, but let me run it. So this is going to be our study area, or not. I apologize for the technical issue. Let me see if I can show you like this. No. Okay, I will not make it run, unfortunately. I don't know why. However, our study area is around the city of Sendai in Japan, on the northern east part of Honshu Island. And the data that we will be using, as I've mentioned before, are going to be the GRD data, so the level 1 GRD data from Sentinel, and the SLC data, so the single look complex and the ground range detected. These differ in the level of processing, and I will get to that in a few seconds. So why do we use Sentinel-1 for events like this? And this is because with extreme events like this, it is likely that they will increase in number and severity as a consequence of climate change. And satellites, such as Sentinel-1, are playing an increasingly important role in understanding and tracking such huge storms. Sentinel-1 is especially valuable in this, as it can see through clouds and can therefore help map, for example, the scale of flooded areas immediately during the event, and as well as damage, for example, afterwards in the absence of cloud-free imagery. In this exercise, we will use these 2 data sets, and the event that we want to look at, as I mentioned before, is the landfall. It's on the same day as the landfall of Hagibis occurred, and we will be looking at the city of Sendai and its surroundings. And the event happened on the 12th of October. For the first part, we will be using images from 6th October and 12th of October, so directly during the event. And for the second part, for the damage assessment, after the waters or flooding has subsided, we will be using images from 24th of September, 6th of October, and 18th of October, so 6 days after. Okay, we move on. So, to start with the exercise, I will today, because we have a lot of ground to cover today during this webinar, so I will not cover the details of preprocessing that we have covered already in other webinars. So you might have attended other webinars where we discussed preprocessing of GRD Sentinel-1 data. These steps are generally very standardized and they're always the same. Here you can just see the graph that we will be using. For those who don't know what the graph is, I will explain it when we start the exercise. So I will still show you the graph, but I will not go into too many details. If you do miss this information, then you can see in our previous webinars, for example, the deforestation monitoring in Paraguay with Sentinel-1, or flood mapping in Malawi with Sentinel-1, or water body mapping in Germany. All of these include exactly the same chain, or almost exactly the same chain of processing with reasoning and with information about each of these operators. So just one more word about the ground range detected, what actually the data type is. So it's focused data that has been detected, multi-looked and projected to ground range. And the phase information in this data is lost. Phase information is generally used for coherence estimation, as we will do in the second part of the exercise, or for example for interferometry, subsidence monitoring and so on. But for flood mapping we do not need it anymore, so that's why we use the ground range detected data. Okay, so let me go out and let me go to the RUS virtual machine, but maybe I will first show you the website. So this is our RUS website that I've shown you a screenshot before, and here when you already have your account, you can either create a Copernicus SSO account to log in, or if you have it, you can log in here. And you will be directly logged into your RUS service tab, where you can go to your dashboard, from which you can see the active RUS virtual machines that you have, or request a new one in case you don't have it, or for example chat with our support desk. So I have my virtual machine, so I will just click here, access virtual machine. There we go. So this is how the RUS virtual machine looks. It's basically a remote desktop that you're connected to through your browser. I can increase it to be a full view. And we will be using today the Snap software, so let me open it. Okay, so let's start with the first exercise. So this is the Snap window. We have the Product Explorer right here. This is where all our products that we load into Snap will be shown. Then here we have some other tabs that I will show you in a second. So let's open some products. I will use a session that I have saved previously. Normally, if you want to open a product, you will click here. You will navigate to the folder where the product is saved, and you will open it. I need to open two products, and just to make situations easier, I created a session file. That I have here, so it will load my two products. As I mentioned before, the first one is from the 6th of October and the second one from 12th of October. So let's now open them and have a look. So let's open the intensity VH polarization. For both images. And then I can go to Window, once the second one opens, and I can put them next to one another. Okay, there we go. So we can see that while the windows are synchronized, my images or our images are not corresponding to exactly the same area. I can also have a look here at the world map. When I zoom in, I can see the footprints of my two images. So we have a slightly larger area on the later image, so on the one from the 12th during the event. Okay, and if I zoom in to this area here, this is the area that we are interested in. Okay, and you can definitely see a change here. Okay, so you can definitely see a change in this region here, and this is due to the fact that there is now a flooded area in this region, which we can see as very dark. So the dark color here, of course, or dark values here, low values here, let's say, correspond, of course, to the ocean, and here they correspond to the flooded area. So how can we now pick out or enhance the visualization? So first, of course, we have to pre-process the data, as I was already mentioning. So you've seen the graph on the slide before, but let me just open it here. So I have these two products, and now I want to process them both. In Snap, you can use this graph builder to build your process flow, and then you can use the batch processing to process multiple products with this flow. So let me open the graph builder and load the graph that I have prepared. If you want to prepare a graph yourself, this is how you start. So you start with read and write operator, then you right click and you select whichever operator you wish to use. For example, for us, the first one would be apply orbit file. You connect and you continue in this fashion. So, and of course, always there will be a tab for parameters for each operator that you add. But let's load a graph that's already created. There we go. So this one is relatively long. As I said, I will not go through the steps. I will just show you how it looks and refer you to one of our previous webinars. The only step that is not covered extensively in the previous webinars, or it's not included in the graph in previous webinars, although it is also addressed, is the linear to dB, at which point the backscatter coefficient is converted into a logarithmic scale into decibel values, which go approximately from -40 to +5 in values. And basically they offer us enhancement of the visualization. But you will see that in a little bit. Okay, so I have my graph, and now I would want to go to the batch processing and process both of my images. So let's close it. And let's go to batch processing. Remember, I already saved the graph. If you are creating your own graph, you first have to save it, so you can later load it here into the batch processing. In the batch processing, in general, you want to load all the open products, for which you can use add opened, if the open products that you have are all of those that you want to process. Okay, so here you can click refresh to get some additional information, and here we want to deselect keep source product name. This button, if we keep it selected, it will cause the output of the processing to be named exactly the same as the input, which in this case it wouldn't matter to us because it will be saved in a different format and in a different folder. However, if you save your outputs in the same folder where your inputs are, you might cause your inputs to be overwritten. So let's select it just as a precaution, and let's load the graph. Okay, so now you can see that for each operator I now have a tab. I don't have the visualization of the graph anymore, but I have for each operator I have one tab present up here, and I can now set my my processing parameters. So in apply orbit file I don't need to change anything. I will not explain what these operators are. Again, I will refer you to one of the previous webinars. However, I will tell you what values to set here for our specific case. So for the orbit file, apply orbit file, we do not need to set anything. The same goes for the thermal noise removal. We also do not need to set anything. For calibration as well. Speckle filter. So speckle is basically inherent noise present in our images, and it's caused by random constructive and destructive interference, and we can get rid of it by several methods. One of the methods is the speckle filter, which is basically spatial moving window, and there is a number of methods that we can use. So here we will use the Lee filter with window 3x3. The speckle filters almost always result in some degradation of resolution, not pixel size but resolution, because they will blur and average our values over a certain area. There is other methods, such as, for example, averaging, multitemporal averaging, which is of course only applicable if your application is not time sensitive, and you can, for example, select, and your area does not change. So you can select 10 images, and you can then process them and average them to level out this random noise. That gives you the best results without degradation in the resolution, but for us, of course, that is not an option. Maybe it would be an option for the pre-event picture, but definitely not for the event during the image during the event, because we only have one. So we use the Lee filter, then we go to terrain correction. Here you might know that we need to terrain correct SAR data due to the severe effect that terrain has. Our study area is also very mountainous, so there will be even more pronounced effects. And what we want to do here is we want to change the digital elevation model to SRTM 1 second, which is higher resolution than the 3 seconds, and also it better represents the coastal areas. The SRTM 3 seconds unfortunately does not cover well all the coastal areas, and also basically causes all the coastal areas to be lost. So we will select the SRTM 1 second, and then we go to the map projection, and in the map projection we will select the UTM VGS8004 automatic. So the normal projection that was selected here, which is called VGS84DD, this is the latitude-longitude standard projection. However, for our region there might be quite significant distortion already, so that's why we want to use UTM. And the automatic will, because UTM has a number of zones, and not always we know which zone we should select to have the best or the least distortion, but here this method will choose the right zone for us. So now I chose it, and you can see that here I have now UTM zone 54. Okay, and now I will go to subset. So finally, we do not need to process the entire image. It's not necessary. We are interested in a relatively small area or smaller area, and we can therefore subset our product. We will subset it using geographic coordinates. We can also use pixel coordinates. However, for Sentinel-1, I would recommend always using geographic coordinates, as pixel coordinates will differ between products, and you here use it in batch processing, so you're processing multiple different products. So let's go to geographic coordinates. Here I can zoom in like this, close to the footprint of my first product, and I here need to input polygon in a well-known text format. So how does that look? It looks like this. So I can copy it from here. And I can click update, and now it appeared here on my as a footprint. Maybe some of you wonder how to get this polygon. I can show that a little bit later. Okay. You can also in the in the subset you can also do band subset, which is meaning if you have more bands than you need, you can also just click on one or two to select them to be processed, and all the rest will not be processed. If I do not select any, by default all of them will be processed. Okay, and the last step is the linear from to decibel. Here we do not need to select anything, again just the band subset if we want to. Okay, and here we would just need to make sure that we are setting the correct output directory, and there is no sense of changing the name, as the name change will only apply to the first product that is processed, and if we do batch processing and process multiple products, for the next products this will not take effect, and it will default back into this name, which basically consists of the original name of the product plus suffixes for each of the operators and prefix for the subset operator. Which also gives us a good chance to make sure that we know what operators we applied to our product. Okay, and I would click run, and both of my products would process in approximately 5 to 8 minutes. We don't want to do that now, as we would have to wait, so I'll just close the window and I will load the pre-processed products. Okay, there we go. So we have the two products that are processed. Let me close these view windows. And let me open these just to have a look. You can now see also that here in this picture we now have this new footprint of the two new products that were processed. And let me open both of them. So now you can see that we are more focused on our area. We have a very smaller area, and also you may notice that the image is differently oriented. This is due to the fact that finally we have, so before when we were processing the image and when I was showing you the original data, the data was still in radar geometry. When we applied terrain correction and when we applied when we basically reprojected the data into a known coordinate system, now we have the sort of true representation. Before, the data was mirrored to the side, which is due to the radar geometry, due to the way how the data are acquired, and also partly due to the way how Snap is showing the data, as it always shows the pixel that was acquired first in the upper left corner. Okay. So that's just an explanation why the data are now turned differently, and this is our two images. So this is obviously the picture during the event, and this one is prior to the event, and we can clearly see all of these changes. But still, why we can see them, we might want to have some more clear idea or delineation of the changes. So what we will do now, we will actually stack the products together. So we'll go to, radar, co-registration, co-registration, stack tools, create stack. So this menu is relatively similar to the one that we seen in the batch processing. We again click on add all opened, and we just need to delete the two previous ones because of course we only want to stack the processed products. So we only have the two. Then we click on refresh to get some more information, and we click on create stack, sorry. Here the stack is created, so the product, there is two products. One will be dedicated as master and one will be dedicated as slave. We want to select the optimal master, so we click here. And we want to also choose which way the slave product will be resampled to the grid of the master product. So here we select a nearest neighbor, which does not change the values. And here we will check or select the initial offset method as product geolocation. We do this because if we were, so if you are using data or stacking data that have already been terrain corrected, geolocated, and had their orbits applied or updated, you will always want to use the product geolocation. If you're stacking data that have not been terrain corrected, you in general want to use the orbit initial offset method, as this one will be the more precise. But however, for the product geolocation, we already used a digital elevation model, which makes it even more precise than the orbit information. Okay, and finally we will go to the right, where we can select the name, change the name a little bit to reflect our product, for example. But you can select any name you like. I will not run it, so you will see later what I have named it. And like this, you can create the stack. Just make sure here that you save the output data into the appropriate directory, and we would click run. Again, this takes relatively short time, about a minute, but we will not run it. Okay, so let's open the processed product. I'm sorry. Okay, so in the next step, we have now the processed product, and if I go, expand it and I go to bands folder, I can now see that I have 4 bands instead of 2, and I have 2 bands for each of my dates. So I have 2 bands, so VV and VH polarization for the 6th of October, and VV and VH polarization for the 12th of October. Okay, let me now just close all my previous products. Okay, close one by one. Very well. So now I have just this one product, and the first thing I want to do, so at the moment my no data value is assigned as 0. This is okay for most of applications. However, for the DB, 0 is a valid value. That's the first thing. And secondly, it's also a relatively high value. And unfortunately, when you do color composites, this will appear as white. And we don't necessarily want that, so let's change the no data value into NaN. You can do this by going to raster and data conversion and set no data value. Here you just need to add something to the name, otherwise your original input is going to be rewritten. And here we select, of course, no data value will be used, and then which no data value we want to select. You can also select a different value, such as -999, for example, but we will select NaN, not a number. Okay, and I would click run. Okay, so this is this one. Again, I will not run it, I'll close it and open already processed data. Now, this doesn't look any different than the one before, but if I compare, if I have a look at the no data value, so right click here and I click in properties, here you can see the no data value is used, it's selected, and no data value is 0 in the original one. I can change it also here manually. However, I would then have to rewrite it for each band separately, which I don't really want to do. So I did it through this tool. And here, if I go to the same band, now you can see that no data value is set to NaN. Okay. Now, in the next step, we want to get rid of our C area, just to have a clearer visualization. So let me open the band to show you what I mean here. So this all is an ocean area. It is not really causing us any problems. However, maybe the visualization will be nicer if I remove all of this area, and then I will have a better histogram stretch and I will see better the differences on land. So to do this, we will use the mask, sea land mask that Snap has, and it can also apply a vector or shapefile as a mask. And so first we need to load the shapefile. So if I select the product 6, so the one that I have assigned the no data to, and then I go to raster, then I go to vector, I'm sorry, import an Esri shapefile. I have a shapefile that represents the coastline of Japan. So let me load it simply, and it will be overlaid over my image here. So now I can use this shapefile to mask out the area that lies below the shapefile, to mask out the area that lies outside of the shapefile boundaries. So let's go to raster, masks, land seed mask, and here I make sure that I have product 6, so the one that has the no data applied, selected, that I have the correct output directory, and in the processing parameters I can select here, use vector as a mask. And since I have loaded the vector, it's present here, and I don't have to do anything else. If I wished to mask out all the land mass, I can invert the vector, but I don't want to do that. So this is how I would run the mask. And let's open the processed image again. Okay, so you can see that it's still overlaid by the mask, but now the ocean values are marked as no data. Just to get rid of this mask, because I will not need it anymore, I will go to vector data folder, right click on the mask and select delete, or on the vector. Okay, so this is now my final image. And now I can do some visualizations. So what I want to do, I want to actually do multi-temporal composite that will really bring out the flooded areas, and I can identify them better. So to do the composite, I will right click and I go to open RGB window. And here I will select the VH band before the event as red, the VH band during the event as green, and the VB band before the event as blue. Okay, now here we have our image. You can see that we would assume that all the purple areas correspond to flooded areas. Well, we can assume flooded areas, of course, but basically what you can deduce logically is that all the areas that will have higher backscatter before the event than during the event will appear purple, because those will correspond to the red and blue part of the spectra. Sorry, red and blue bands, not part of the spectra. So these will be shown as purple. And then all the other places or the other pixels that will have higher backscatter during the event than they had before the event will appear greenish or green, as those are the ones that we have assigned the VH band during the event to the green color. So now let's try to say why this is the case. So we have used the VB band during the event as the green part of the spectra, and let me open it also. Okay, so here, so this is the VH band that we have used as green band. And you can see that all the water areas, or presumed water areas, are very, very dark. Why is this? So water in general in SAR, or calm water, calm open water, appears very dark due to the fact that the incoming signal or the outgoing signal from the SAR hits the water and is reflected away from the sensor. Basically, it's a mirror reflection. SAR is very sensitive to any sort of surface roughness. So this causes the mirror reflection, where all the incoming radiation is actually reflected away from the receiver or from the receiving sensor. Why VH? So in VB, of course, we will have a relatively similar result, however, not quite so clear. And this is due to the fact that VB there occurs some return backscatter. But in VH, over calm water surfaces, there is no depolarization, which means that there is very little, very little backscattered radiation in the horizontal polarization. However, there is still some, depending on the water or surface roughness of the water. For example, if there's a larger water body with some waves and so on, there might be still some returning radiation from this in the VV part of the spectrum, of VV polarization, I'm sorry. Okay, so this is why we have used the VH, because it picks out better or shows us better the flooded areas. Let me close these views. So here we have this nice visualization. You can notice that most of the other areas are sort of greenish tint color. Also, we have some green areas here, for example, on the beach. And this can be caused by a different determining effect of SAR, or by different property of the surface that determines the backscatter of SAR, which is the dielectric constant. Which is the dielectric constant, which basically means that surfaces, or as one of the things that it means is that if you have a wet surface or wet soil, it will have a higher backscatter than very dry soil, because it will have a higher dielectric constant. So of course, during the event we had a lot of rainfall. In some areas of Japan it was even 860 millimeters of water during 24 hours, which is very hard to imagine. So of course the land is, or the soil is going to be very wet and saturated, even if it's not submerged currently. So that's why we have slightly higher backscatter in the bare soil areas, such as, for example, this area around here around the airport, and there's a beach or some sort of other probably bare soil area. So we have then a very bright response from this area during the event, much more bright than during the than before the event. It can also be caused, for example, by submerged vegetation, because in submerged vegetation there will be a higher reflectance during the event due to the fact that you will have a coronal reflectors. This of course depends on the specific properties of that part or of that such submerged vegetation, but basically you will have a mirror reflection on the water surface, and then again reflection back to the sensor from the submerged trees and so on. So we have then bright response in that respect. So it can result in both. However, in VV usually we don't observe this effect. We observe it more in HH, which we don't have available. In HH is very good. HH polarization is very good for monitoring submerged vegetation, and also VV can give some information. Okay. So this is our flood map, let's say, but still we don't have them delineated. So how do we do this? We can this time we will use a difference between these two bands. So we will use the difference in backscatter between the two dates to delineate our areas. So in this case it will be delineating open water areas. So let's right click on our final product, and let's go to bandmouth, and let's calculate the difference. So let's give it the new band a name, for example 06 October 12 October, and we will do first VH polarization. We will deselect the virtual, and we will go to edit expression, where we will subtract these two bands. So we will subtract the band during the event from the band before the event. So first will be the 6th of October minus 12th of October. Okay, there we go. So this is the resulting map, You can again say that this is not quite so clear, but actually the flooded areas are appearing very clearly in this image. And we have to do the same now also for VV, or we can do the same now also for VV. Okay, very well. And now we have both calculated. Let me just visualize them next to one another. So I go to Window and Tile horizontally. Move this window here, so I have actually 3 windows next to one another. There we go. So here is the 3 that I have calculated. This is corresponding to VH, VV difference, and the RGB composition. And what we can now do is we can either use band math or we can just use visualization to pick out the areas, to create a binary map basically of our submerged areas. So you can see, of our flooded areas. So you can see that the white makes a difference where the backscatter was higher before than it's during the event. So that's the bright in both of these. And then we have some areas where the backscatter is darker, which correspond to, which basically means that the backscatter was darker or lower before than is during the event, which can potentially in VV represent these submerged vegetation, as I was mentioning before. Okay, so let's just visualize it or create new bands. So what we can do here, we can create a new band that we name F as flood, for example, BH. We select virtual, and we will use a conditional statement where we will threshold this difference band, and we will basically say if diff BH is larger than 6, then assign 1, else assign 0. So why am I selecting 6? This is purely to the basically estimation or trial and error from the map. It will not always work with the same amount. You have to test it. It will differ for different locations and different events. But I choose 6 decibel difference as the appropriate one. Okay, so select OK. Okay, and there we go. And now I have a binary band where I have marked as white or as 1 all my open water areas in this case. And then let's make another band from the VV. That will be if diff VV. Here I will set the threshold a little bit lower, so it's larger than a 5. Then assign 1. Otherwise, I will have another condition. If diff VV is larger than -5, then I will assign 0. Okay, so otherwise I will assign -1. I will explain that in a second. Let's create the band. Okay, and here now if I go to the visualization of this one, so here it's clear, ones flooded areas, zeros potentially not flooded areas. Here in VB it's a little bit different. I have 3 different values, and I want to actually set them as discrete values, and I want to set values that are -1, which are the low ones, to red. So those would be the ones that I suspect might be a submerged vegetation, so the difference is below 0 or below -5 actually in this case. Here I will assign black, so this area is the area that I suspect there is no flood in VV, and here as 1 or as bright white I have the flooded areas. You can see that I have slightly less of them in the VV than in the VH, and this is due to the fact, as I've mentioned, that the open water surfaces are better visible in our VH band due to the depolarization or lack of depolarization on open water surfaces. Okay, so this is our flood mapping. You can export the bands using file and export them, for example, in GeoTIFF, and I will at the end show you some visualization in QGIS. And this would be the end of our flood mapping exercise. It's if you are interested in flood mapping, you can check our other webinar on flood mapping, which uses a slightly different method. And let's move on to the second part of this webinar, which will be looking at the damage assessment. So now we have looked at where our flooded areas were during the event, and now we will try to see where our which buildings were or which areas were damaged. Okay, so I will restart Snap. I don't need to save anything, but that depends on you, of course. And I will reopen Snap again. And let me just go back into my presentation and show you the other parts. So here in this second part, we will be using a single look complex data. I have been talking about them before, and they are focused georeference and georeference using orbit and altitude data from the satellite, and they are in slant range geometry, and they also contain the phase information, which is important for this step. The first part of the preprocessing, when we generate coherence, is generally always the same. So we don't really need to go through it as it was covered in other webinars. For example, you can have a look at the urban classification in Germany webinar, so LAN06, where you can find all this information. So let's go to load the data. So here, so I uploaded actually all my products, almost all my products already, but my input products here are these 3. So these are the original SLC data that I will be using. And coherence, how do we map damage using coherence? We can identify presumably damaged areas if we looked at the loss of coherence. I will not explain what coherence is. Again, I will refer you to other webinars that we had, such as the urban mapping in Germany, because we are actually running very late on time. So I will just follow this. So basically for coherence, you always need 2 images that contain phase information and are acquired from the same orbit by the same satellite, of course, and so by the same satellite. And generally here we have them available 12 days apart. So we have the 24th and 6th, which is before the event, which means that the coherence in many areas is going to that are non-changeable, such as the areas that are not vegetation or water, will be very high. However, during the event there might be some changes to the surface and also to these otherwise not really changing areas such as buildings, roads, bare soil and so on, which generally have high coherence. And what can happen is that the changes will cause a loss of coherence. So for the image that has one image, for the pair that has one image before and one image after the event, we will see a loss of coherence. Okay, so when we process them, I will quickly just show the graph. In the graph builder, you have seen it already on the image. So this is the graph that we use. We read both of our products of the pair. We will apply a top-star split, apply orbit file. We will co-register them, and then we calculate the coherence, and then we apply the burst. So this is where we are at the moment. And now let's just quickly see how the result of this processing looks. Again, if you're interested in knowing what each of these operators does, I would refer you to the other webinar. So these are our outputs. It's a coherence band only, and it looks like this. If I open the second product, you will not really see a lot of difference at this point. They look both very similar. You can see the bright areas are the areas with very high coherence. For example, the ocean area here, you can see it has very, very low coherence with just some random noise here. But the city areas have very high coherence in general. Okay, so the next step that we need to do, I will only show this for one of the images. We need to go and we need to multi-look the image. So what is multi-looking? Multi-looking refers to a process that we use to basically get rid of some of the speckle noise, which is even more pronounced in SLC data, as they have the original SAR resolution. And you can see that the image appears sort of stretched. This is caused by the fact that the pixels in the SLC data are not square. They are not square. And what we want to do is basically we want to average a certain amount of pixels to achieve a square pixel. And also by that we want to limit the speckle. So how do we do this? We use the multi-looking tool. So we go to tools, radar, multi-looking. Here we select the product number 4, for example, because this one already have the multi-looking applied. So we select product number 4, and we make sure that we have the appropriate folder. Then we go to processing parameters, and we just check here. We will not change anything here. We will have only one band, so we don't need to subset. We want to have a square pixel, and here we can see the number of looks, which means how many pixels in what direction we average. So in the range direction, which is the direction perpendicular to the direction of the treble of the sensor, we want to average 3 pixels. In the azimuth direction, which is the direction of the treble, is 1. So you can see that in the end, if we do this averaging, we receive a mean square pixel of 13.5 meters. Okay, so this we would run for both of the images. Again, I will not run because I have them already, and I will just open a processed one. So that's this one with the ML at the end, and you can see that the shape of the image has changed a lot. So if I change like this, now looks very different. Basically now we have square pixels. In this case, of course, it should look like this as well. It just would, in a zoom in, not have square pixels, but Snap is not capable of visualizing pixels that are not squared, so he treats them as squared, all of them, so that's why the image is stretched. Okay, so we have the multi-looked images, both of them. And the next step that we need to do is, again, we need to create, so we need to georeference our product as we have done before, because again, you can see that it's actually turned around opposite to the result that we had from the first exercise. So we use a terrain correction again. I have shown you already how it looks in the previous exercise. It's exactly the same one. So we will go to geometric, terrain correction, range Doppler terrain correction. Here we will be careful to select the multi-looked products, and in the processing we will select again SRTM 1 second. I have explained why in the first part. We can now here change the pixel spacing from this 13.98, which is sort of, or 96, which is sort of random, to, for example, the first round numbers 14 or 15. And then we can check here again the UTM automatic. Okay, now we would run. This takes again about a minute, so I will not run today anything, so I will close it again. I would repeat the same process for the second one, so let's now load the result. There we go, so this is my result, and now again, as in the first one, I would want to create a stack. We will again be calculating difference between the coherence before and after. Before we were calculating for the flooding difference between the backscatter coefficient. Now it's going to be between the coherence. But anyway, we need to create a stack again. So we'll go to radar, co-registration, stack tools, create stack. Now we can first actually just close all of these products because we will not need them. There we go. And we can close now, we can choose now add opened because we only have the two that we want to use. And we can click refresh, create stack. Again, we set basically the same parameters that we set in the first part of the exercise. So we set, we find optimal master, nearest neighbor as our resampling type, an orbit, product geolocation. Remember, we do product geolocation always when the product is terrain corrected and projected. And then we go to write, select our home directory or output directory and our output name, and click run. And we will end up with one product that will be called, in this case I named it Coherence with the 3 dates stack. And now it includes 3 bands. I will leave it there, but it contains 2 bands. Basically, it will be the coherence from the first image, coherence from the second image. Do not pay attention to this band now, or I will delete it actually. Okay, and we will create it together. So these two are now the 2 coherence bands that are terrain corrected and stacked together. Let's go to radar, window and tile horizontally to compare them visually. Okay, so let's zoom into some interesting area. For example, here, that's the one that you know appeared green in the first one. So we can see actually that in the pair before the event, we had much higher coherence in this beach area here and then close to the airport. So the airport is located here. We had much higher coherence here than we have in the with the pair that has one image before and one image after. So we have actually significant loss of coherence in this region. Just to make sure, we can click on this image now here and we can see the histogram, and from the histogram we can apply the same histogram stretch also to the second coherence pair. There we go. So now we know that the histogram stretch is exactly the same for both of the images, and we can actually visually compare them. So you can see the loss of coherence, and now let's quantify it using a band map and create again a binary band with our predicted or detected areas of potential damage. So let's go to band math, and we will name our new bands ICD, which stands for interferometric coherence difference, and we will deselect the virtual because we want to save the band physically, and we will go to edit expression and subtract the second coherence from the first one. So first we select the coherence before the event, and then the coherence during the event, and and subtract them from one another. Okay, let me close all of these and let me zoom in a bit. So this is the city of Sendai. We can see that if we look at the difference, of course the positive difference here is where the coherence was higher before the event than during the event. So this is some areas where there is some loss of coherence, the bright ones. But we want to be a bit conservative with the threshold we select for this, because there might be other changes. So actually, let's select the threshold somewhere around 0.5. So I'll just quickly visualize this. Or actually, let me load a palette that I have created previously, and I will explain how it works a little bit. Let me put on full screen, okay. Then we do not want to stretch, we want to use the palette that I created. And now we can see, so this is the main part of the coherence, sort of randomly around 0. There will be a lot of random values in this as well. And then we want to choose the significant difference, which is marked as threshold 0.5, which we marked here as white, and 0.75, which is very high difference already, because the coherence, of course, goes from -1 to 1, sorry, from 0 to 1 in percent, basically, you could say. And I can see the very bright red spots where some sort of really significant difference occurred, so around 0.75, which I can then sort of assume are some detected damaged areas. It will always depend on how you play with this threshold, and it will also depend, of course, on some Turing knowledge or the knowledge of what is in the location. So this is the second part of the exercise, and let me just quickly show you a visualization of both. Again, you could export this output into GeoTIFF here. Okay, let me select it, and then I can export it to GeoTIFF, and then import it, for example, to QGIS and create some maps, such as the one that I will show you now. So let's close this, and let's open QGIS. And I will only show you the visualization. So this is the area, this is the city of Sendai, this is the agricultural areas that were flooded during the event. And we can see in blue, of course, is the open water flooded areas. And then in red, if you zoom in, we can see which areas the damage that we detected corresponds to. So here is the airport. Right, here is the airport, and here we have some parts damaged in the city. We would have to have clear look to see what they correspond to. So for example, here it's on the river, so if we zoom in, we will see that it's actually a bridge. Here we have some wave protection here in the harbor, so that apparently has also been damaged, as well as these areas here potentially being damaged. So this can give us a very good idea of sorry about that, of where the damage occurs. And here we can see the footprints of my two products. So the red one, of course, corresponds to the damage, so this is the area for which I have calculated or estimated the damaged areas, and the blue is the flooded areas part. So this is it. I know that it was a lot and it was a long webinar, and it was quite a lot of information. So this is just a quick summary. I hope you've enjoyed the webinar. Again, RUS service provides a free, although I understand a slightly geographically limited, cloud computing environment and virtual machines. And the idea is basically to solve any problems with computational power storage and also knowledge. So you can access the RUS EO help desk, the webinars, which are open to all. So the webinars can be attended and watched, of course, by everybody. and they can be repeated also on your local computers. The next takeaway would be that Sentinel-1 can map floodings. You can watch this webinar, or you watch this webinar, or you can also watch our first webinar that was on flood mapping with slightly different method, also with Sentinel-1. And then you can also detect potentially damaged sites as a result of flooding or other events such as earthquakes and so on, using Coherence. Of course, you cannot detect a single house, for example, because the resolution does not allow for that, but you can detect damaged areas and so on. So if you wish to repeat this webinar, you can use this code. It's called HAZA06 to request the webinar to be uploaded to your virtual machine if you already have one, or if you request one, this can be done as well. And you can check for our future events either on our social media, so Twitter, LinkedIn, Facebook, and also on any of our recordings on YouTube. And you can check also for all our future trainings on our RUS-training.eu, and the recording should be available in the beginning next week, so you can go through it again if you wish. And I would also ask you, once we log out, to please fill in the survey. It helps us to improve, and it also gives us an idea what your opinion about the webinar is, and it's very valuable. So please take a couple minutes to fill in the webinar. Okay. Thank you for watching. I hope you've enjoyed, and I'll see you at some of our future webinars or face-to-face events, hopefully. Okay, so have a nice rest of the day, and bye-bye.